Hello, in this lecture, we're going to discuss model validation. Now, in previous lectures, we've already built our first model, which would be the decision tree model. Now, we're going to want to know if the model is any good. And so by wondering if the model is any good, we're going to ask, did our model overfit or underfit the data? In other words, was it a good model, or did we underfit the data and make a model that wasn't quite as good as it could be, or did we overfit the model and learned the data, the training data, without actually learning the underlying pattern? Let's take a look at what I'm referring to here. So let's assume we have this data set right here. Now, with this data set, let's take a quick look, and we have a data set here, and you can see that there's a trend kind of here, right about like that. So if I were to say, let's assume that this is a data set that says how much electricity you might use to heat your house during the day. And this would be like an average value over time. And you could say, like, in the early morning when you wake up, you haven't turned on any gadgets like your stove or whatever. You could see that you probably use less energy in the early morning. And then as the day goes by, you've got the dishwasher running and the washing machine and all this other stuff. So during the day, certain parts of the day, you could see, well, you probably use more, and then as the night goes on, you don't wash your dishes at night, and then things go down a bit. So this would be something like that. And you can see there's sort of a trend. So if I were to say, like, at 6 o'clock at night, assume that this is 6 o'clock, you could say, okay, well, probably the guy's going to be using, a lot of electricity. And in the early morning, maybe not so much. So we found an overlying, a trend here. Now, you could say, well, not all of the data points follow exactly this trend, and that's probably because there's other factors that our data set doesn't have. In this data set, we just have what time of day do we have, but there might be other things, like maybe you have guests over, and so you're using the stove more because you're cooking a big Thanksgiving dinner, or perhaps you are, you're not home or something, and so maybe you have less electricity being used. So there's other factors that our model is not taking into account because the data may not be available. So this is a model you can see here that there's a trend, but the trend is not perfect, but that's okay. But we're looking for the big picture here. So what would a optimal model look like? So again, I've just shown you this. This would be like what an optimal model would be. It's not perfect, but it's capturing the trend. But now, if we want to see what an underfit model might be, you can see here that we have a straight line. Let's assume that we have a straight line model instead of this one here. And now, if I were to say, okay, in the early morning, how much electricity would we use? Well, our underfit model would say, okay, not very much. Okay, well, fair enough. But then we say, well, what about during the middle of the day? Well, okay, again, it's underfitting this thing, or it's underpredicting because it's a straight line and we're missing this trend. But then we say, well, midnight, how much electricity are we using? Well, our model is going to say you're using lots and lots of electricity at midnight, when in reality you're not. This model is an overly simplistic model, and it's not predicting the trend that it goes up and then begins to taper it towards the end of the day. But now, again, this is our optimal model, but now we're going to take a look at our overfit model. So an overfit model, in this case, will perfectly fit our training data. So you can see here that we're completely fitting every single point And this doesn't make any sense at all, because you can say, well, geez, here we are at 6 o'clock in the morning, we don't use very much, but then 7 o'clock in the morning we use more, and then all of a sudden we have 8 o'clock and we use less again, and then we have I don't know, we start getting into late at night, and it's just like a snake here. And we're covering every single point. This is not covering a trend. This is overfitting this data. And this model doesn't make any sense at all. It's perfect for our training data, but if I put any new data in that we've never seen before, this model is going to be next to useless. So overall, we have this data set here, this top data set, and we have an underfit model, we have an optimal model, and we have an overfit model. And you can see all three of them here. So clearly this optimal model has identified a trend, but it does have a little bit of error associated with it, but that should be expected. You're not going to be able to predict perfectly unless you have a perfect knowledge of all the input variables, and you never do. So this guy here assumes that your time of day fits things perfectly. It doesn't. So this guy is wrong, and that's really the most dangerous, but at the same time here we have an underfit model. Now, how do we protect ourselves from that? So we're going to talk about that in just a moment. But again, here we have the three scenarios, and at this point we have just a predictor variable and an output. This would be like a numeric value, but it can also follow the same trend for a classifier. So you can see here that, again, if we're looking at maybe electrical usage over time, that would be something like this. But you may also need to classify like in the iris problem, what type of iris do you have? A Setosa, versicolor, or virginica? Or does a person crash their car or not crash their car? There's all sorts of categorical variables, and you may have to differentiate between the two. So here we have an underfit model right here, and that guy is, mostly correct. I mean, we got all the green guys up here and the red guys are below, but we miss a big chunk of them right over here. And we miss a big chunk of these guys. Now, here is one where it's a good model. Now, we're not perfect. We've got some of these red guys are slipping in where the green one is, and we've got some of the green ones are inside where the red area is. But for the most part, this line does a really good job of differentiating between green and red dots. Now, an overfit model would be right here, where you're trying desperately to get every single one, and that's not making any sense at all. That's unlikely to be a useful model, and it's not something that is, it just by looking at this does not suggest that this is a decent model. It is likely an overfit model. Now, what we will do is we're going to figure out how do we test to see if our model is any good. So what we will do is we usually will have what's called a training data set and a test data set. So this will be a way that we can we build a model on one data, but we hold some of it out and we test on it. So the model gets to see data that it's never seen before. So let's give you an example of that. So let's open up R, and I'm going to first show you how we can break data into two sections. So right here we have a data set, and let's assume that we have it would be 8 people. Amy, Bob, Kathy, Don, Eddie, Frank, Gloria, and Henry. So we got 8 people here, and we're going to put those guys into a data frame. So let's copy these guys and paste them into R. So we've created an array of these names and stuck them in a variable called name, and then we're going to create a data frame and we're going to put name in there. So if I type DF for the data frame, you can see I've got Amy, Bob, Kathy, Don, Eddie, Frank, Gloria, and Henry. These 8 people. So how do I split this thing up so that we can train on one data set and test on another? Well, I have some sample code here, and what we're going to use is a random number generator. So the random number generator will use a seed value, and if you don't tell R what the seed value is, it's going to use the internal clock, and so it will be, for all intents and purposes, truly random. The reason why I like to use a seed value is it allows me to reproduce my answers. So anyways, we have here a seed value of 1, and we're going to set the random number seed to 1. Now, if you set this again to 2, you're going to start off with a different random starting position. But we're just going to go with this. And what we will do is we're going to create a flag. Okay? So here's what we do with this flag. We're going to create an array that we're going to call flag. And what we're going to do is we have true and false, and these are Boolean variables for R. So we have the true and we have the false. And we're going to ask R to give us a random sample, and we're going to say, hey, by the way, we have 8 rows, so please give us 8 rows. And what we want you to do is take a random sample where 65% of the data will be true and 35% of the data will be false. So let's run this code and see what happens. So we've just run it, and now we have a variable called flag. So if I type in flag, you can see, let me move it up a little bit, you can see that it is true, 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 false, false, false. Okay, let's run another one. Let's run it again. Flag. Let's move it up so we can see it. And now we have true, 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 false, true, false, true. See, the number, they have changed. And every time I run this, it's like rolling dice. Every time I run this, I'm going to get a different set of data. Let's run it again, just for fun. So then you have here false, false, true, false, false, or true, false, true. Okay, there we have it. So for the most part, we're going to probably end up, given the sample size here, it's possible that we get more falses than true, but for the most part, we're going to get more trues because we have 65 versus 35%. So let's run this thing, and we're going to say what we are going to do is our training data right here will be set to when the flag is true. Our test data is when the flag is set to not true or false. So we're going to create 2 data frames, a train and a test. So let's run those guys and let's print them off. So when I run those, we started off with these variables. Oops. We started off with Amy, Bob, Kathy, Don, Eddie, Frank, Gloria, and Henry. A, B, C, D, E, F, G, H. Okay. And you can see here that we got 3 variables in our training set, Kathy, Frank, and Henry. And Amy, Bob, Don, Eddie, and Gloria are in our test set. So we would build a model using these 3, and then we would test the model on these guys right here. And if our model is any good, our accuracy on our test set should be pretty close. It may not be as good, but it should be pretty close to this guy right here. And then what you usually will do is you'll run this thing several times. Once you've decided on a model that you like, then you're going to go back and you're going to say, okay, I've just ran a training and a test set. Let's do it again. And you should consistently see. Now we have, well, in this case, we only had one guy, Eddie. So Amy, Bob, Kathy, we built it on all these guys and we tested on Eddie. This is why you do this a lot of times. So I usually do it 4, 5, 6 times. And I like to see if my model is any good based upon lots of different. Now we have Amy, Bob, Frank, Henry, and then Kathy, Don, Eddie, and Gloria. Let's do it one more time. And now we have Bob, Don, Eddie, Gloria, Henry, and Amy, Kathy, and Frank. So you can see how this is working. I'm constantly got one data set that I'm going to build a model on, and I've got another model that I'm going to test on. So this is the overview of how, why we test. We have a holdout sample, and the holdout sample is going to allow us to guard against overfitting or underfitting. We're going to talk later on about how we can guard against that, but this is allowing us to test it. So starting off, we have to be able to break data into training and test, and that's what we just did here.